Alright, so this is our second to last review, unless you're taking the final. We end with Chapter 5, and this is the last bunch of stuff on derivatives, and we start something new in Chapter 5. So let me just kind of jump into this review. Like all the reviews, I'll do both the evens and the odd problems, and if you could do every problem on the review, you should be fine for the test. So problem 1 gives me a graph and asks me to find the absolute maximum and absolute minimum, and the highest point on the graph contains the absolute maximum, and the lowest points on the graph contain the absolute minimum. The absolute maximum and absolute minimum are y values, and usually we'd write I'll just write the answer. So we'd say there's an absolute maximum, I'll abbreviate that, of y equal 8, which occurs at x equal to negative 2. And then there's an absolute minimum, the y coordinate of the lowest point, of y equal negative 1, which occurs twice. I need to write that 2x values at x equal negative 1 and 1. And that's kind of all we're looking for. There's no algebra for that problem, so there's not a lot of room to give you partial credit. 2 and 3 are asking the same questions as number 1, but they don't give us a graph, they give us a function. So the first step to find the absolute maximums and absolute minimums, if you're given a function over a specific interval, is to find the derivative and find any critical numbers that are within that interval. So I took the derivative of x cubed is 3x squared, the derivative of minus 6x squared is minus 12x. I'm going to take the derivative and set it equal to 0. Pull out my common factor of 3x. Set each of the factors equal to 0. On this one you divide by 3 and you get x equal to 0. This one you add 4 to both sides and get x equal to 4. Since both the critical numbers are within the interval negative 1 to 5, I have to include both of them in my computation. Once you get the critical numbers that are between the given numbers, you make a table. I usually put the first two numbers as the numbers given in the given interval, and then beneath them I put any critical number that's in that range, and both 0 and 4 are in that range. And then what I was doing is getting the y values, and usually I turn my calculator on, get to the y equals screen, graph the function, set my window up to accommodate the beginning number. So I want my window to go between x equal negative 1 and x equal to 5. I don't absolutely have to see my graph, but I think I don't see everything here. I'm going to get my y values, and then maybe I'll tweak my window just to show you that I'm okay. So second calc value, x equal to negative 1, so y equals to negative 7 there. And I just have to type the number 5 and hit enters, and y equals negative 25. And then type in 0 and hit enter to get y equal to 0. And type in 4 and hit enter. I get y equal to minus 32. So in order to get a good window for this, my y's have to go down to at least to minus 32. So if I change my y like to minus 40, which is less than minus 32, and sketch my graph, you'll see better what we need. So for this function, that point right there is the point 0, 0. That's where the absolute maximum is. There's an absolute maximum of the y coordinate of that point, which is 0, and which has an x of 0. And then down here is where the absolute minimum is, And there, that's from the point 4, negative 32, because negative 32 is the smallest y value. So if I do second calc value 4, you'll see that that's the point 4, negative 32. There's an absolute minimum of negative 32 when x equals to 4. So let me just try to write that up as an answer now. So for an answer, I'm going to write it more or less like I did the last answer. So there's an absolute max of y equals 0, and I'll say when x equals 0, and that's just taking that point. And then there's an absolute min of y equal negative 32 when x equal to 4. And so once you get the table complete, you take the points that have the smallest and the largest y values and kind of break them up to your answers. And the points that I tried to circle there that I shouldn't have, and the point that I didn't do anything with, because their y values they're between the smallest and the largest, those points don't show up in my answer at all. For 3, I'm going to have to write uglier y answers, and I don't want decimal answers. So if you start to do number 3 and one of your absolutes has a y equal to an ugly decimal, then you're going to lose some points, because I want the E answer. So first step in number 3 is the same as the first step in number 2. Find the derivative. I need the product rule because of the multiplication. So I need to go the derivative of 2x squared times the e to the x function unchanged plus the derivative of the e to the x function times the 2x squared unchanged. The derivative of 2x squared is just 4x. So this first piece is going to be 4x e to the x. The second piece, the derivative of e to the x is just e to the x. So the second piece is going to be e to the x times 2x squared. I need to do lots of common factoring. I'm going to factor out an e to the x. I'm going to factor out a single x. And I'm going to factor out a 2. And that's going to leave some stuff left over. So I'm going to write f prime of x. I'm going to write a 2, a single x, and an e to the x. From this first term, I took the entire x out, the entire e to the x out, but there was a 4 when I factored a 2 out. I have to divide the 4 by 2 to figure out what's left, and what's going to be left there is a 2. I'm going to bring down the plus sign. I took the entire e to the x out from the second piece. I took the entire 2 out from the second piece, but when I factored out an x from this piece, there was an x squared. There's still an x to the first left over. So to the right of my plus sign, I'm just left with an x. Now that I have my factoring, I set the derivative equal to 0. And that's going to cause me to go 2x equal to 0, e to the x equal to 0, and 2 plus x equal to 0. For the 2x equal to 0, you divide both sides by 2 and get x equal to 0. E to the x can never be 0, so there's no solution there. And for this 2 plus x equal to 0, you minus 2 from both sides, and you get x equal to minus 2. Because both of those numbers are between negative 3 and 1, they belong in my table. So now I'm going to do my table. My first value is going to be negative 3. My second's going to be 1 from the interval. And then I'll tack on my critical numbers of 0 and negative 2. I'm going to get all of the y values by hand real quickly here, and then I'll get decimal versions on my calculator. I need the decimal versions to be able to answer the questions, because the e versions, it's not going to be obvious what they equal to. But now for each of these, I'm going to get e values, because I need e values in my calculator, in my answer. So I'm going to go 2 times negative 3 squared times e to the negative 3 to get the y value for that point. This is going to be 2 times 9, because negative 3 squared is 9. So it's 18e to the negative 3. And I'm going to make that have a positive exponent. So I'm going to write that first y as 18 over e cubed. Eventually I'm going to get a decimal equivalent for that. But I'll get all these nice ugly y's first, and then I'll go for my decimal equivalents. To get the second y, I take that x and plug 1 in. This is going to be 2 times 1 squared, which is 2 times 1, which is 2. And e to the first is just e. So that y, the y that goes next to 1, is going to be 2e. The third one is the only one my calculator could do okay. This is going to give me 2 times 0, which is 0, times e to the 0, which is 1. That's 0 times 1, which is 0. My calculator, if I use the value feature on my calculator, could give me that y. And the last one, I'm going to go 2 times negative 2 squared times e to the negative 2. This is 2 times positive 4, so that's going to be 8 e to the negative 2. And I'll write that with a positive exponent, so I'm going to write that as 8 over e squared. So those are the proper y coordinates, the kind of y coordinates that I have to include in my answer, but they're not helping me understand which point is the point for the maximum and the minimum. So now I'm going to pull out my calculator, do my y equals, enter the function, so 2x squared second ln e to the x, set my window to go from negative 3 to 1, because I look at the original points and they go from negative 3 to 1. I'm going to make my y's go from the 10s again. I don't know if that's good or bad, but it just is. It's probably not even the best window. It probably needs to be, well, I'm not sure what it needs to be, but I can get the y values real quickly here by going second calc value negative 3. And for negative 3, I'll say that's 0.90. So this decimal, 18 over e cubed is about 0.9. Now I'm going to go 1 and hit enter, and 2e is about 5.4. It doesn't matter how I round these, as long as I can tell which y is the biggest and which y is the smallest. And then I get 1.08 for the negative 2. So it looks to me like I know now where the smallest and the largest points y values are. This looks like to be the absolute minimum, because in this column of y's, 0 is smaller than any of those other numbers. And it looks to me like that's going to be the maximum, because in that interval of those 4 y's, that's the biggest number. So now I can write my answer. There's an absolute max of y equal to 2e, which occurs when x equal to 1, and there's an absolute min of y equal to 0, which occurs when x equal to 0. When I did the section, I got a little bit lazier when I wrote the kind of the word answers to these questions. So if you wind up getting a little bit lazier, and as long as you tell me the important parts, you separate the x and the y coordinate of the point, and say that the y part is the absolute max, the y part's the absolute min, you can definitely abbreviate this write-up a little bit. All right, now we've got a word problem. This chapter had a lot of word problems, so we're kind of stuck with them. And each of the word problems we're going to do should be a word problem that you've already seen, just with different numbers, and barely different numbers at that. So number 4 gives me that campground owner. He's got some fencing. He wants to make a rectangular field bordering a river. So you need the river. So I can simulate my river. Here's my river with blue. And the campground owner is going to build 2 fence sides that are going to be perpendicular to the river and one that goes parallel to the river. So it's my nice rectangle. And I think I tell you which side to make the width. Make the width be the side of the fence that's perpendicular to the river. So that 2 widths and 1 length need to be constructed. So this is going to be a length. This is going to be a width. This is going to be a width. So for this area, it's a rectangle, and regardless of the fact that I'm only building 3 sides, it still has an area of length times width. The perimeter is 2L plus 2W, but the perimeter that I'm building 2 W's in 1 L. So the perimeter equation is going to take into consideration that I'm not building all 4 sides. The area equation, it's still a rectangle whether I'm building 3 sides or 4 sides. This whole area that's being enclosed is still a rectangle that has an area of length times width. The 500 meters, because it's a linear number and not a square number, represents the perimeter of the amount of fence that I have, which is going to be the value of the perimeter. So the equation that I'm going to get from my diagram is going to be 500 equals 2W plus L. And in part A, I'm asked to write an equation for the length of the field. I'm just going to take this 500 equals 2W plus L, and I'm going to minus 2W from both sides and get an equation that's solved for L. So I'm going to write 500 minus 2W equals to L, and that's going to be my answer for part A. The length written in terms of W is 500 minus 2W. To do part B, I've already wrote an equation for the area of the field. Area is length times width, but that's not going to be the best formula because it has too many variables. So I'm going to change this L to 500 minus 2W. I'll get the area as 500 minus 2W times W. I'm going to clear that parentheses by going 500 times W, which is 500W, and minus 2W times W, which is minus 2W squared. That's what I'm going to write for my answer to the next part. That's the area equation for this. Now I'm asked to write the domain, and the domain has to be the form that the width is between a lower and an upper number. And if I think about this, there's 500 meters of fencing. If I'm building 2 widths, the most either one could be is 250, because if you use each width at 250, you'd use up all your fencing. So just divide the amount of fencing by 2. That would tell me what each width can be at maximum. And of course, the lowest the width can be is 0. You couldn't build less than 0 because that's physically impossible. So the answer that I get for W, the width of my field, has to be somewhere between 0 and 250. If you had 250 widths, then you'd use up all your fencing, and of course you can't be less than 0. Now comes the calculus part. Find the value of W that leads to the maximum area. To do this, I'm going to find the derivative, so I'm moving on to part D. I'm going to take the derivative. A prime equals 500 minus 4W. I'm going to set the derivative equal to 0. I'm going to add 4W to both sides, so I get 500 equal to 4W. And then I'm going to divide both sides by 4. I think that gives me 125 equals to W. So what I have is a critical value, and in addition to my critical value, I have a domain restriction. So really, my original function, if it was given to me like the last problems, it would have been written like this. Area equals 500W minus 2W squared And then next to it, it would be the domain is 0 to 250. So when I go to do my table to find out the value of W that's the absolute maximum, I'm going to make a table. I'm going to write a 0, a 250, and then the critical number of 125 in the table. And those are going to be my widths because the x in this equation is a W. So this is going to be the width. And to the right, to the left of the equal sign, I get an A instead of a Y, and an A stands for area, so the Y's are going to be my area. So what I'm going to do is take these three values, plug them into the area function before I took my derivative, and get the Y values. I'm trying to find the absolute maximum. The Y value that has the largest number is going to be the maximum area that I can enclose. The corresponding X value is going to be the width that gives me that area. So I'm going to need to enter this function on my calculator. So clear 500. I have to use X. My calculator won't handle W so well. So 500X minus 2X squared. Change my window to go from 0 to 250. I don't really care so much about my Y's. I'm going to graph it and not see much of the graph. But what I have set up is good enough for me to get the Y values. So now second calc value, type in 0, and I get 0. Type in 250, and I get 0. Type in 125, and I get 31,250. If I wanted to see the graph, my window would have to have a Y that's at least 31,250. So like if I made my Y go up to 35,000, I can see the maximum. That's the point 125, 31,250. And you can see it there. So there's the absolute maximum. The Y value is the area that's enclosed, and the X value is the corresponding width. So the maximum area that we can enclose is 31,250 square. I don't know if it's feet or inches or meters quite yet, when the width is 125. So now I'm going to go to answer the last few parts of this. The value of W that leads to the maximum area is the X coordinate, and it's in meters. So the value of W that leads to the maximum is width, or W, equals 125. And because the units are in meters, I'm going to write meters. The maximum area is this 31,250. So area equals 31,250. And it has to be in square meters. Those two values I didn't need to do any algebra for because the vertex, or the maximum, had that number waiting for me. For part E, to find the value of L that leads to the maximum area, what I need to do is take this 125 and plug it in for L up here. That I can do from the main screen in my calculator, or I can do it in my head. So second quit, 500 minus 2 times 125, and you get 250. So L is going to be 250 meters. You can abbreviate meters if you care to. So that's everything for part D. In fact, that's everything for problem 4, so that all the answers are kind of staring at you right now. All right, guaranteed to be one of those. There's a chance that the problem on the test isn't the river one. I consider the problem where you're building all 4 sides of the fence, similar enough to this, where that might sneak its way onto the test. So make sure you can do both the building a fence problems from section 4.2, I think it was. All right, so it's like cut and paste. I didn't like the way I did number 5 the first time, so I'm going to redo it. So number 5, we're going to have a square piece of 8-inch by 8-inch metal, and we're going to cut X-inch squares from the corners. And the question is, if I start with a square piece of metal that's 8 inches by 8 inches, so this is my initial piece of metal, it's 8 inches by 8 inches, and then we're going to be cutting corners out of this square box that are x by x. So I'm going to cut a corner out here. I'm going to cut a corner out here. I'm going to cut a corner here and cut a corner here. And each of my cuts are going to be x by x cuts. And then after I make the cuts, I'm going to fold up and make a box. And I've kind of constructed this already. This was my 8-inch by 8-inch sheet of paper. And I cut out from each corner an x by x inch cut. And what happens when you do that is you can then fold up the sides and make a box. So what happens when I start with an 8-inch by 8-inch piece of metal, if I cut x-inch corners out, I'm able to make a box without a top, and the height of each of the box is going to be x for each of the sides here that I cut up, and I fold them up. This box is going to have a height of x. These sides that I cut out x by x from, what's going to leave me, it's going to leave me with 8 minus 2x by 8 minus 2x for each of the sides. Because what happens, the sides start off with 8 inches. I cut 2x inch cuts from them. I'm left with 8 minus 2x's. So from this distance from here to here, it was initially 8 inches, but I took this x inch away, I took this x inch away. I'm left with 8 minus 2x. So what I'm going to have, this is my diagram. What I'm going to have is a box that I need to find the volume for. And in order to find the volume of a box, you have to multiply 3 lengths. The length of each of the parallel sides times the height. What I'm going to have to do is label these sides as lengths, width, and heights. And the x is definitely going to be good for the height, because when I fold it up, it becomes the height. The dimensions on the bottom, it doesn't really matter which I call lengths and which I call widths. But parallel sides going to be given the same names. So what I'm going to have is 2 lengths and 2 widths on the bottom of this. But they're the same. They're both 8 minus 2x, so it doesn't matter really which I call length and which I call a width. So what I've done is I've created a box, and ultimately I'm going to want to find its volume. The volume of any box, whether it has a top or not, can be found by taking the measurements of the 3 individual sides and multiplying them together. So this 8 minus 2x I might call the length. This 8 minus 2x I might call the width. And any of these x's are going to be the height. So the volume of this box that I've created is 8 minus 2x the length times 8 minus 2x the width times the height of x. Part B wants me to find an equation for the volume of the box. This is all I would need for Part A, is that diagram. I don't need to start talking about the volume until I get into Part B, but I started doing Part B while I was doing Part A because it just made sense to do. In order to get a nice answer for Part B, I'm going to clear the parentheses that I've created by going 8 times 8, which is 64. 8 times minus 2x is minus 16x. Minus 2x times 8 is minus 16x. Minus 2x times minus 2x is plus 4x squared. I'm going to clean up the parentheses, combine like terms, and write it in a nice order. I'm going to write the 4x squared first. The 2 minus 16x's I'm going to combine to a minus 32x. And the plus 64 I'm going to leave as a plus 64, but I'm going to write it last. Now I'm going to multiply everything through by x to get rid of that x after the parentheses, and I'll get my best answer for Part B. The volume equation is volume equals 4x cubed minus 32x squared plus 64x. So the volume of this box can be generated by that equation. Done with Part B, moving on to Part C. In Part C, we have to think about the domain of my box, or what values can x possibly take on. I know that if I'm making a cut, the smallest cut I can make is 0. That's making no cut, and I wouldn't get a box if I did that. because I'm making 2 cuts and I'm starting with 8 inches, if you divide 8 inches by 2, you get 4 inches for the maximum cut. You can't make 2 cuts bigger than 4 inches because that's more than 8 inches. So for the domain of this, we're going to say it's between 0 and 4. That's it for part C. Part C, we want to find the value of x that makes the volume the largest. So what we have is we have a volume equation that's equal to 4x cubed minus 32x squared plus 64x, and we want to find the maximum value that the volume can be over the interval from 0 to 4, because that's the feasible domain for this function. And I find a maximum value by simply creating a table, putting the edges of the domain as numbers in my table, along with any critical values that are between those values of x. So in order to finish up this step, I need to do some work. And so that work's going to be some calculus. I know that in my table that the x's represent the length of the cut, and the y's are going to represent the v, which is the volume for that length of cut. In order to get an answer, I'm going to have to improve my table by adding some numbers to it. And the numbers I'm going to add to it are any critical numbers that are between 0 and 4. To get the critical numbers between 0 and 4, I have to find the derivative. And to find the derivative, I'm simply going to use the general power rule. Sorry, I had to shut my blind because it was getting an awful glare on this, and I didn't want that to show up forever. So the derivative of my function, I'll take the derivative of 4x cubed, which is 12x squared, the derivative of minus 32x squared, which is minus 64x, and the derivative of positive 64x, which is positive 64. Let's set my derivative equal to 0 to get my critical value. So I'm going to go 12x squared minus 64x plus 64 equals to 0. I'm going to pull out a common factor of 4 to make my work easier. So I'm going to get 12. 4 times 3x squared minus 64 divided by 4 is... do that in my head, but my brain is starting to die on me, so I'm going to do 64 divided by 4 on my calculator and get 16. Plus 16 equals to 0. Be nice if I could factor this more. That's bottoms-up factoring. I can do bottoms-up factoring quickly, but I'm assuming that you're not really wanting to do bottoms-up factoring. And another way to get the values of x that I need is to pull out the quadratic formula. So instead of factoring this using bottoms up, I pulled it down unfactored, and I'm going to use a quadratic formula to get the values of x that make this parentheses equal to 0. When I go to solve this, the common factor that doesn't have an x doesn't give a critical value, so there's going to be no solution there. This, I'm going to use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. And into that formula, I'm going to put a equal to 3, b equal to negative 16, and c equal to positive 16. So I'll go x equals negative from the formula, and then negative 16 for the b. Because the b is negative, it has to go in a parentheses. And then plus or minus the square root of negative 16 squared minus 4 times 3 times 16 all over 2a, which is 2 times 3. The numerator, the double negative 16, turns into a positive 16. And under the square root, I have to do parentheses negative 16 squared minus 4 times 3 times 16. And I get a 64. And in the denominator, 2 times 3 is 6. So I'm almost there for my critical numbers. This simplifies to be x equals 16 plus or minus 8 over 6, because the square root of 64 is 8. I'm going to separate this into x equals 16 plus 8 over 6, and x equals 16 minus 8 over 6. For x equals 16 plus 8 over 6, you get 24 over 6. which is 4. And for x equals 16 minus 8 over 6, you get 8 over 6, which is 4/3. So those are two critical values. 4 is already on my table, so I don't need to re-add it to my table. And 4/3, because it's in between 0 and 4, needs to be added to my table. So the optimal cut is going to be either 0 inches, 4 inches, or 4/3 inches. I need to find out which of these cuts is the optimal cut. And I do that by taking the volume equation and plugging these values of x into the volume equation. I can plug these values of x into the volume equation easiest by using the value feature on my calculator. For one of the three, I'm going to get an ugly decimal and not really be able to use my calculator answer, but I'm going to get what I can out of my calculator by going to my y equals and entering 4x up arrow 3 minus 32x squared plus 64x. I need to make my window go from 0 to 4. I just did this problem and messed up, so it's already there. And I wouldn't generally know what the y's should be, so I'd probably generally make my y's negative 10 to 10 and get a picture where I can't see the graph real well, but I can get the y's real accurately. So now I'm going to graph this and do second calc value, type in 0 and get 0, type in 4 and get 0, type in 4 divided by 3 and get something I'm going to write off to the side because it's not really an acceptable answer. I'd probably round that, but that's all my calculator can do for me. If I want to see my graph better, my y max needs to be bigger than 38 or 37. If I change my y max to that 50 that I had it before, you'll see the maximum really well. This graph has a maximum when x is 4/3 and y is 37 point something or other. To see that maximum on my calculator, I just evaluate it at 4/3 and I can see perfectly that the optimal cut is 4/3 inches, that the volume it's going to give me is 37.925926 cubic inches. I'm going to improve upon this answer by putting a fraction answer in my volume column. To get that fraction answer, I have to take the value of 4/3, plug it in for x, and I need to do that on my main screen because my main screen gives me the ability to make decimals into fractions. So back to my main screen, and I'm going to go 4 times parentheses 4 divided by 3 up arrow cubed minus 32 parentheses 4 divided by 3 squared plus 64 times 4 divided by 3. And I better get this number exactly, which I did. Actually get even more exact. I get more decimals, but it's exactly that to that many decimals. Math, enter it, and I get a better number for my y column. I don't want decimals in my y column if I can't help it for this problem. So now I can answer part D. The value of x that makes the volume the largest is x equal to 4/3. And because my cuts are in inches, I'm going to say x equals 4/3 inches. Find the maximum volume. That is a decimal version of the maximum volume. That's a fraction version of the maximum volume. And I prefer the fraction, but I live with the decimal. But regardless if you give me the fraction or the decimal, you need to have units. And volume always has cubic units. And because the lengths are in inches, it's going to be cubic inches. If you gave me a decimal, I'd probably write the fraction in it, but I'd live with that. All right, so that's problem 5. Let's move on and do problem 6, which is a price elasticity function. For problem 6, I'm asked to make a price elasticity function for this clothing company. So this clothing company manufactures t-shirts. They sell the t-shirts for 20 bucks. The price demand equation for the t-shirts is given by price demand is 70 minus 2p, where the price D of p is the number of t-shirts sold at price p. Part A says compute the price elasticity function, In order to do a price elasticity function, I need to know the derivative of the price demand function. So before I jump into doing part A, I'm going to find the derivative of the price elasticity function. And that's a real easy derivative to take. The derivative of 70, because it doesn't have a letter, is 0. The derivative of minus 2p, because it's a first power term, is its coefficient of minus 2. So now I can find the price elasticity function real easy. The price elasticity function involves taking the formula and replacing two things in the formula with information that's specific to the problem. You leave the negative p from the formula in the numerator, and then after the negative p there's a time sign which I can replace with a parentheses, and after the time sign or inside the parentheses I'm going to put d prime of p, which is negative 2. In the denominator, I'm asked to put d of p, which is 70 minus 2p. I can simplify this numerator if I think of this as negative 1p times negative 2, and that will be positive 2p over 70 minus 2p. This is a perfectly great answer for what the price elasticity function is in part A of number 6. If you wanted to, you can factor out a common factor of a 2 in the denominator. And if you factor out a 2 in the denominator, you'll be left with 2 times 35 minus p. And you could cancel out the 2's, and that would give me probably a better answer, an answer that's easier to work with. So for part A, the better answer would be the price elasticity function is p over 35 minus p. It's likely that the problem that we get on the test that asks for this, it probably won't even be able to factor and cancel. If you missed the factoring and canceling and gave me this, I'd give you full credit. So done with part A. Part B is real easy. Part B just wants me to take whichever version of the function I came up with an answer in part A and change the p to 20. And this we usually live as a decimal. So I'm going to do e of 20, and I'm going to use my easy function. I'm going to go, it's 20 over 35 minus 20. That comes out to be 20 over 15. That reduces by 5. 20 divided by 5 is 4. 15 divided by 5 is 3. 4/3 would be fine for an answer. And if you wanted to give me a decimal version of 4/3 and round it to 2 decimals, I can live with that as well. So I'll say these are both okay. It almost is easier to work with the decimal than it is the fraction when we do the part D of this. But I'll live with either. We'll get slightly different answers to part D if you use 4/3 in your computation than if you use 1.33. But I'll live with either. I think in the videos I consistently round it to 2 decimals, so I'm going to work with this answer. For part C, is at a price of $20, which is this price, is demand relatively elastic or inelastic? If this number is between 0 and 1, it's inelastic. If it's bigger than 1, it's elastic. Because it's bigger than 1, we say it's relatively elastic. Which means a percent price increase will cause a bigger drop in demand. For part D, how much would demand change if the price of t-shirts was raised by 25%? Demand will go down by more than 25% because prices, it's relatively elastic. To find out how much demand will change, I'll take the number that I got in part B, the 1.33 or the 4/3 if you don't want to round it, times the decimal version of this percent, which is 0.25. So I'm going to go 1.33 times 0.25. And I'm going to get 0.3325, and I'm going to change that decimal into a percent, and that's going to be 33.25%, which this says is a 25% price increase will cause a 33.25% demand decrease. That means it's relatively elastic because you get a bigger drop in demand than the price increase. All right, so that's everything for problem 6. That would be my answer to part 6D. This would be my answer to part C. And one of those two answers for part B would be okay. One of these two answers for part A would be okay. All right, so we'll keep going here, and hope we're getting close to the end. 2 word problems, and then some implicit differentiations. So 7, 8, and 9 just want me to do implicit differentiation. So I'll do that. The derivative of x cubed is 3x squared. The derivative of 2xy, because it's a multiplication, I have to use the product rule. So I'm going to have to do the derivative of 2x times the y function unchanged plus the derivative of the y function times the 2x unchanged. That's going to be the product rule for that. I already took the derivative of x cubed. I'm going to take the derivative of this on my next stage. The derivative of 3 on the right side is 0. So now I'm going to get 3x squared. The derivative of 2x is just 2. So the middle piece here becomes 2y. The derivative of y is 1, but because I took the derivative of a y, I have to tack on the dy dx. I'm going to leave the 2x over here equal to 0. And then I'm going to minus these from both sides. So I'm going to minus 3x squared minus 2y minus 3x squared minus 2y. And on the right-hand side, that's going to give me a minus 3x squared and minus 2y. This is the thing that I have left on the left-hand side. I'm going to multiply the 1 and the 2x and get a 2x dy dx. Because this is a monomial and not a binomial, when I divide to solve for dy dx, I'm going to do 2 fractions on the right-hand side as opposed to 1. But you can definitely do 1 fraction on the right-hand side. So on this step on the right-hand side, you could write negative 3x squared minus 2y all over 2x. If you write that on the right side, then you can't reduce, and this would be a perfect answer for what dy dx equals. So this would be completely okay to do the right side like that, making 1 big fraction. If you make 1 big fraction, you can't reduce it. I made 2 little fractions. On the left-hand side, I'm canceling out my canceling out my 2x's, left my dy dx. This fraction reduces. Then minus 3 over 2 doesn't reduce, but x squared over x cancels out, and you get left with an x. For this fraction, the 2's reduce, and you're left with a y over x. These are both correct answers, and I really don't care which one you give me, just as long as if you do the way I did it, you reduce properly, and if you do it this way, you don't reduce, because written as a single fraction as opposed to 2 separate fractions, it's not reducible because they reduce differently. Just checking my work. Looks good. Alright, so 8, there's no product rule in here, but so I have to use implicit differentiation. The derivative of any e function is the e function times the derivative of its exponent. So what I have to do to finish up the derivative of this first piece is take the derivative of 4y. The derivative of 4y is just 4. But I have to add to this a dy dx. Done with the derivative of this piece. Now I'll take the derivative of the minus 2x, which is minus 2. And I'll take the derivative of x squared, which is 2x. Now I need to solve for dy dx. I'm going to add 2 to both sides and get 4e to the 4y dy dx equals 2x plus 2. If I factored out a 2 on this left side, right side, it'll make the canceling that can happen be easier to see. To finish up solving for dy dx, I need to divide by 4e to the 4y. If you missed the common factor, I doubt that I'd take a point off, but I'd probably write it down for you. Once I do this division on the left side, I just have my dy dx. And on the right side, these and these can cancel. It'll leave the numerator as an x plus 1. The denominator will be 2 times e to the 4y. That's probably the best answer for problem 8. If you had this for an answer, or this with a 2x plus 2 in the numerator, I'm sure I'd live with it. I'd just probably write in the right answer and not take any points off for you. But factoring and canceling is generally the goal that we have when we're writing a derivative. We want to simplify it the best we can. Last, in implicit differentiation. Oh, we still have more problems than I thought. The derivative of y squared is 2y. Because I took a derivative with a y, I have to tack on a dy dx. To do the derivative of 2xy, I need the product rule. I'm going to do the derivative of 2x times the y function, the y term, plus the derivative of y times the 2x unchanged. So that's not done with the derivative, but that's how I'm going to do the derivative of that using the product rule. And then my equal sign, to the right of the equal sign, the derivative of 3x squared is 6x. So let me finish up the derivative of the product rule that I hadn't finished yet. The derivative of 2x is just 2. I leave that y alone. The derivative of y is 1, but I have to tack on a dy dx because I took a derivative of a y with respect to x and leave this 2x. I'm going to minus 2y from both sides, and I'm going to leave this piece written as 2y times dy dx. This piece I'm going to write as 1 times 2x is 2x dy dx. And the right side I'm going to have a 6x minus 2y. I'm going to factor out a common factor of a 2. On the left side, I need to solve for dy dx, so I'm going to pull out a common factor of dy dx. There's a bigger common factor than dy dx, but if I factor it out, it's going to make it harder to solve for dy dx. So on this step, I did 2 common factorings. I factored out the dy dx, which I'm trying to solve for, on the left side, and I factored out a 2 on the right side. Now I can divide by 2y plus 2x. And when I do that, on the left side, I have my dy dx, which is my goal to find that. On the right side, now in the denominator, I'm going to pull out that common factor of 2 that I kind of hadn't factored out yet. And these 2's will cancel. And the best answer for number 9 would be dy dx equals 3x minus y over y plus x. All right. 3 more problems. Question 10 wants me to find an equation of a tangent line. It gives me a point but not a slope. So I need to find the slope. I find slopes of tangent lines by finding the derivative and plugging the values of the point into the derivative. So eventually I'm going to use the y minus y1 equals m times x minus x1 formula. But I can't use it yet. I have the x1 and y1 because I have a point, but I don't have the slope. To get a slope of a tangent line, you plug a number into a derivative. So I'm going to find the derivative. The derivative of x squared is 2x. The derivative of y squared is 2y, but I have to tack on that dy dx. The derivative of 13, because it doesn't have a letter, is 0. I'm going to solve for dy dx. I'm going to minus 2x from both sides and get 2y dy dx equals negative 2x. And now I'm going to divide both sides by 2y. On the left side, the 2y's cancel. I'm left with a dy dx. On the right side, the 2's cancel. I'm left with a negative x over y. Now I can find the slope. The slope is going to equal, I'm going to plug in a 2 for the x and leave the negative sign there, and I'll plug in a 3 for the y, and that's the slope that I'm going to need then. So my slope is going to be negative 2/3. Now I'm going to take those values and plug them into the y minus y1 equals m times x minus x1 equation. I'm going to get y minus 3 equals negative 2/3 times x minus 2. I'm going to leave the left side y minus 3. On the right side, I'll go minus 2/3 times x, which is minus 2/3 x, and minus 2/3 times minus 2, which is plus 4/3. And then I need to add 3 to both sides, and I'm not feeling really motivated to deal with the fractions, so I'm going to use my calculator to finish up the 4/3 plus 3, even though it's not that hard to do by hand, but it's easier to do like this. So I'm going to go 4 divided by 3 plus 3, and math, enter, enter, and I get 13/3 for my right-hand side. Could definitely have gotten that without my calculator, but it's easier on my calculator. So that would be the answer for number 10. So we have 2 more problems left in the related rates word problems. So problem 11 is that you take a pebble, drop it into a still pond, and then it forms concentric circles, and they get bigger. Mine didn't particularly get bigger, but the concentric circles keep getting bigger and bigger, and so if I read this is the diagram. A pebble is dropped into a pond, causing ripples to form in concentric circles, and the radius of the outer ripple, which is what I've drawn here, is increasing at a rate of 2 feet per second. So at 1 second, the radius is going to be 2 feet. At 2 seconds, the radius of the outer ripple is going to be 4 feet, and it doesn't look bigger. This was supposed to be bigger. At 3 seconds, the radius of the outer of the concentric circle is going to be 6 feet. And so what it's given to me here is that how the radius is changing with respect to time, which is dr dt, is 2 feet per second. When I move on to the second sentence, or third sentence, when the radius is 6 feet, that gives me when r equals to 6 feet, at what rate is the total area of the disturbed water changing? And that's the derivative, that's dA dt. That's how is the area changing with respect to time? And this is what I'm trying to solve for, because it says at what rate is the total area of the disturbed water changing, and that's what the dA dt is. So this is the givens. Dr dt is 2 feet per second. The radius is 6 feet. I'm trying to find dA dt. And for all of these circles, the area is pi r squared. In order to get the problem solved, I need to take the derivative of the area equation with respect to t. So the derivative of a would generally be 1, but because I'm taking it with respect to t, I tack on a dA dt. The right-hand side would generally have a derivative of 2 pi r. I just multiply the 2 by the pi and lower the exponent by 1. But because I took the derivative with respect to t, I have to tack on a dr dt. Now I can plug the numbers in that I have. I'm going to leave the left side dA dt. I'm not going to write the 1. And on the right side, I'm going to write 2 pi. And then for r, I'm going to write 6 feet. And then for dr dt, I'm going to write 2 feet per second. I'm going to multiply the 2, the 6, and the 2 and get 24. I'm going to leave the pi, and I'm going to multiply the feets together and get feet squared per second. And that's going to be dA dt. So this is going to be the answer to problem 11. I should probably write some words with it. So I can say the area is changing, probably could say it's growing, at 24 pi feet squared per second. It's important to have the squared units because it's area. Quite honestly, I probably didn't have to use the units in my answer, but the units weren't really cumbersome for my work here, so I included them. When I do problem 12, the units are kind of awkward to use, and I'll probably not use them and just throw them in at the end, and I'll talk through them just like I did in the videos. Alright, so one last problem. Alright, so this is another cut and paste. I made a small math error when I did problem 12 first time through, so I'm doing it again. Let me read through the problem. It says air is being pumped into a spherical balloon at 2 centimeters cubed per minute. Calculate the rate at which the radius of the balloon is changing when the radius of the balloon is 6 centimeters. That's a pretty monstrous problem and a pretty hard diagram to draw. So what I'm supposed to draw is a spherical balloon. A spherical means it's a shape of a ball, and as air is being pumped into this balloon, it stays the shape of a ball. It doesn't distort like some balloons have, not ball shapes. So this balloon, it starts off as just a perfect shape of like a basketball, and as I'm pumping air in, it progressively gets larger. But the whole time as I'm pumping air in, it stays with its ball shape. Not that those really look like balls, but it gets bigger and it stays at a shape of a ball. In this problem, because we're talking about the volume of this balloon or this ball, we're going to need to know the volume formula for a sphere. And that volume formula is volume equals 4/3 pi r cubed. I won't expect you to have that memorized on the test. I'll give it to you. If I don't write it on the problem, you can come ask me on the test if I give this particular word problem. So that's going to be an important formula. As I read through the problem and I start looking at the numbers that are given, the first number I see is air is being pumped into the balloon at 2 centimeters cubed per minute. Immediately when I see an exponent of 3 with the units, I know that's a volume. And this is telling me how the volume is changing with respect to time. That 2 centimeters cubed per minute is a dV dt, or the change in volume with respect to time. That's kind of everything that's in the first sentence. The first sentence only gives me enough to get that dV dt. The second sentence tells me what's unknown, and what I'm solving for, and it gives me another piece of information that I'm going to need. As I read through the second sentence, calculate the rate at which the radius of the balloon is changing. That's the unknown. That tells me what I'm supposed to calculate. I'm supposed to calculate the rate at what the radius is changing, and the rate at what the radius is changing is dr dt. That's what's unknown. That's what I'm solving for. The units on these volume problems with balloons are quite a bit more challenging to come up with than the units for the last pebble word problem. And I'm just going to throw the units in my answer without putting them in the computation, just because it makes it a little bit easier to follow the computation. And I'm trying to find the rate at what the radius is changing. If I wanted to find the rate at which the volume is changing, my units need a cube. If I want to find the rate at which the area is changing, my units need a square. Because I'm just finding the rate at what the radius is changing, that's a linear rate. It's just going to be, the units are going to be the radius is changing in the length centimeters per minute, because the time unit is in minutes and the distances are in centimeters. Because it's not an area, I don't get a square. Because it's not a volume, I don't get a cube. Because it's just a linear length of a radius, I get centimeters to the first power per minute. So that's going to be my units. I'm not going to show units in my computation just to make the work a little bit easier to follow. When I continue reading this sentence, calculate the rate at which the radius of the balloon is changing when the radius of the balloon is 6 centimeters. So that tells me that the radius is 6 centimeters. So when I go to shove the numbers into the formula, I'm only going to plug in 2 when I replace the dV dt, and I'm going to plug in 6 when I replace the radius, and I'm going to solve for dr dt, and the units I'm not going to have in my work. My units are going to be centimeters per minute. So in order to be able to solve for dr dt, I need a formula that has dr dt in it. And so I'm going to get that formula that has dr dt in it by taking the derivative of the volume equation with respect to time. So I'm going to take the derivative of this volume equation. The derivative of v, because it's a first power term, its derivative is its coefficient. Its coefficient is 1, so the derivative of v is just 1. I need to emphasize I'm taking the derivative of a v with respect to t, so I tack on a dv dt. On the right side, to take this derivative, I just multiply the 3 by the 4/3 pi. I lower the exponent by 1 to 2, and I tack on that I'm taking the derivative with respect to t. I'm taking the derivative here of r with respect to t. Now I'm going to clean up the right-hand side by canceling the 3's. This is going to give me, on the left side, I don't really need the 1. On the left side, I have a dv dt. And on the right side, I have a 4 pi r squared dr dt. I could solve this for dr dt by dividing both sides by 4 pi r squared, and then plug 2 in for dv dt and 6 for r. Or I can plug the numbers in and then solve for dr dt. I almost think it's easier to plug the numbers in and then solve for dr dt, so that's what I'm going to do. But absolutely, I could have, on this step, divided both sides by 4 pi r squared. And if I did that, I'd have dr dt solved for, and I'd be able to just shove in numbers. Heck, let me do that. Let me solve for dr dt, just because maybe that's what I've been doing. If I solve for dr dt, I get something messy on the left-hand side, which makes maybe the left-hand side a little more intimidating. But it makes it clear that I have dr dt solved for, and I'm trying to solve for dr dt. So I'll go ahead and do that. So I divided both sides of this by 4 pi r squared. On the left-hand side, I got this ugly dv dt over 4 pi r squared. On the right-hand side, the 4 pi r squareds cancel. I'm left with dr dt. And now, for dv dt, I'm going to plug in 2. For r, I'm going to plug in 6. And I'm leaving my units out just to keep the work easier to follow. If I want to at this point, I could cancel this 2 with that 4. 2 divided by 2 is 1. 4 divided by 2 is 2. I actually almost have an answer, because on the right-hand side, I have the dr dt that I'm trying to solve for. And on the left-hand side, I just need to clean this up. And how do I clean it up? I start cleaning up that denominator. The denominator has a 6 squared that I need to make a 36. It also has a 2 and a pi that were left over after I canceled the 2 with the 4. Now I'm just going to multiply the 2 and the 36 and get 72. The pi is going to stay in the denominator. And I have a dr dt. So that tells me that the radius is changing at 1 over 72 pi centimeters per minute, and that's going to be the answer to this problem. So if I write that answer nicely, I can say the radius is changing, or it's increasing, I guess, at 1 over 72 pi centimeters per minute. When the radius is 6 centimeters and volume is, and the air is being pumped in at 2 centimeters cubed per minute. But ultimately, I just want to know what dr dt is. If you just gave me dr dt, if you gave me that for an answer, I doubt that I'd take points off. I would, prefer you to write your answer with some sort of words, but I certainly can live with a correct number with the correct units without all the verbiage attached to it. So that's the end of the review, and so all we need to do is perfect this. We'll get done with the Chapter 4 test, and then we're done really with derivatives. Chapter 5 is kind of doing derivatives backwards, and it's not the longest chapter. Chapter 3 was definitely the longest chapter that we'll do this semester. So let's rock this test, and come visit me if you're feeling stuck on anything. I want everybody to do well, and I'll stop the video here.